Yeah. Thanks for inviting me to give a talk. As you see, and as you noted already, yeah, the title
Recording in progress.
Yeah. Yeah, the title of my talk today is Overview on Antenna Measurement Methods and their use for R&D of 5G beamforming antennas and material surfaces. Yeah, I'm the presenter, and this was prepared with my associates, Jang Yeon-jo, Yejun-sun, Ji-yeon-jang, and Hyuk-tae. Yeah, I'll get it started right now. Yeah, when you see a gallery of pictures, can you see?
Yes, sir. Yes, sir.
Yeah. Yeah. As I wrote, on top of it, antennas enable us to do video conferencing like this, and you can see many familiar faces here, including me. This is one of the purposes we work on antennas for. Next. Yeah, I also shared several pictures of mine. Yeah, certainly I make antennas like you, and I like you measure the antennas. So a series of activities have been done, as you see from the pictures here. Yeah, spring, summer, winter, and fall throughout a year. I, with my associates and colleagues, work on the designs of antennas and conceptualization of new structures, and for sure, we verify the validity of the design methods by checking them experimentally. That's measurement. Yeah, I prepared several pictures, including the map. So this tells us the location of Incheon. I put the location of Incheon according to the elevation angle and the azimuth angle, which goes with the numbers 52.6 degrees and 126.7 degrees, respectively. So the map itself is the spherical surface, which will be repeated later. So this is where Incheon is located. And what I put this arrow, which takes us to India from Incheon, a passage to India, and the bird's eye view on the campus of my university. Yeah, the outline goes like this. Antenna measurement, what for? That's the first subject. And the second subject is antenna measurement methods and systems. And 3 examples will be exhibited. So there I will deal with the measurement of 5G beamforming antennas and metamaterial lens. So you will see the results of antenna measurement on the basis of a variety of techniques. And finally, I draw conclusions. On your right-hand side, you can see a series of pictures which show a summary of metamaterial and antenna works of mine with my students and researchers from the component side for antennas and the radiating elements and beamforming antenna structures like that. So I think I have a lot of good memories with the Indian researchers through INCAP and other activities. So their work, your work, have motivated me a lot. Yeah, the first topic is antenna measurement, what for? So let me tap into something very basic for the time being. First is antenna measurement, what for? And objectives of the measurement. Yeah, this is a beam pattern, and according to the content of the antenna textbook, you already see the definition of the main lobe and the minor lobes. So lots of parameters to check your antenna performance. This is the main beam, and these are the minor lobes, especially the right next to the main beam. These are called side lobes, and we would like to define the half power beam width from the peak of the main lobe to the points 3 dBs lower. And what you already know how you can characterize your antenna patterns. So free space characterization includes radiation pattern measurement, pointing beam width, etc., directivity measurement, polarization. That includes that goes with the tilt, angle, axial ratio, and cross polarization discrimination. But in the examples, especially the beamforming antennas, I would like to show you the 3 different beams from my antenna. So there you will see, again, tilted angle and transfer characteristics that include gain, efficiency, EIRP, effective area. I should not forget what this picture is given by NSI AM technologists, but what you can also find this picture from other antenna textbooks. Yeah, objectives of the antenna measurement go with the characterization of our antennas. You see a horn antenna. Actually, horn antenna, there are a variety of kinds of horn antennas in geometry, in performances. Yeah, this can be used as source of radiation, or this can be used as a probe, but either will be fine here. Yeah, typical goal of measurement is characterization of an antenna's far field radiation pattern as a function of direction. A typical output is a graphical pattern representation of the field as a function of direction. So there are 4 representative ways to express the far field patterns of your antenna. The leftmost case is a number in a table. So if we specify the amplitude or record the amplitude of the electric field in the air according to the theta. Theta is the angular variable in the elevation cut. So minus 90 degrees, it increases by 1 degree like that. So you can make your own table, or this table is mapped into a rectangular far field pattern plot. So you will see several of them in my experiment case. And this is a planar plot, 2D plot. And also you can watch the far field pattern at the front of the AUT antenna under test. So this is the top view of the far field of an antenna. So you can see a kind of X and Y coordinates used to plot the field, and 3-dimensional far field pattern can be also used. There were 4 different ways to plot the fields, but they come from the same antenna. And the next topic is antenna measurement methods and systems. You will see various schemes of measuring your antennas. Firstly, though there are other ways to categorize the antenna measurement schemes, but I wanted to categorize the techniques into this way. A test range is divided to far field and near field. Actually, near field, at a glance, it is just out of scope, but near field is going to be transformed to the far field through forward propagation algorithm. So you can do that, or using the radiation integral, near field is going to be mapped into far field. So you can save your time by just checking and recording the near field, and using the mathematical transformation, you will get the far field information. And that far field information is going to be compared to the real far field measurement. So in one example, you will see my antenna performance is going to be mentioned with the comparison between the far field measurement and near field to far transformation result, like that. Under the far field, there are direct and indirect methods. And under the near field, you can see planar, cylindrical, spherical, far field measurement schemes. So planar, what these means, the surfaces. Here, I'm talking about the zones. Yeah, we are already familiar with these three zones, especially when it comes to antenna measurement. We are firstly concerned about far field, especially Fraunhofer region or zone. So this criterion is very, very familiar to us. 2D square over lambda. So this is the boundary between the Fresnel or radiating near field and the far field zones. So we try to put our receiving antenna in the far field region to capture the electric field. Then you can make these far field plots. Going down to radiating near field, the Fresnel region, your near field probe or scanner is going to be placed here, and the field recorded in a certain on a certain surface that is going to be transformed using the mathematical near to far transformation, as I mentioned before. And R, this is the starting point of the Fresnel zone or radiating near field zone. Usually, our rule of thumb is 3 times lambda. But in the millimeter wave, oftentimes you can take your near field scanner much further, nearer to the physical aperture of your antenna, which is an AUT, antenna under test. There are 3 field patterns, but these are not far field patterns. These field patterns are captured in reactive near field and at the borderline between reactive near field and Fresnel zone. So still, these fields are not accepted or cannot be compared to the far fields. You can calculate using the numerical analysis tool for your far field, but this is going to grow, and the higher order fields are going to be disappear, and the dominant fields will survive the zone. Then we will use them as the far field. So you remember these criteria, especially R less than 1.6 lambda. There are some controversies to decide the border between reactive near field and Fresnel zone, but practically R less than 1.6 lambda is categorized into reactive near field. Working with the Korea's national radio research agency for millimeter wave power density measurement, we could see several different numbers could be applied to define reactive near field, but actually I should set it apart. Yeah, RF components make the antenna measurement system. So you will see an aqueous chamber that contains antenna measurement system, which consists of components. So you are going to see direct RF system or distributed RF system. Simply speaking, direct RF system goes with the simple vector network analyzer. But if you go with the your pockets are not loaded enough, then you should go with the distributed RF. You buy mixers, you buy amplifiers, you buy synthesizers, and those elements are going to be dispersed and just electrically connected there. That is called distributed RF. You will see what it is. Firstly, this is a direct RF system according to the antenna measurement system providing industry. In the unaqueous chamber, you can see unaqueous chamber, there's a horn antenna and there's an AUT, or you can change them or exchange them. Here, TX antenna, and this goes to a receiver antenna like that. Yeah, TX antenna is usually we use one high gain horn antenna, and both sides are connected to port 1 and port 2 of the vector network analyzer. So vector network analyzer oftentimes turns out to be expensive compared to spectrum analyzer and signal generator. So in my lab, we develop RF sensors as well as the assembly of antenna measurement comprising signal generator and the spectrum analyzer. I myself have my own anechoic chamber on the campus, but sometimes when I want to extend the frequency of observation, then I inevitably set up my own measurement and antenna measurement assembly. It is related to the indirect method, but here, just enjoy the expensive system, which is called the direct RF. So here, what this configuration is quite simple, just because the feeding points of these two antennas within the anechoic chamber are just connected to the 2 ports of the vector network analyzer. That's it. And the others are the kind of accessories, especially the positioner controller is also expensive, including the real turntable and robotic arms. Yeah, this is all about the direct RF. Next is indirect or distributed RF. So you now see inside of the bolts and nuts of the vector network analyzer have been disassembled and they are distributed like this. You can see a mixer here and another mixer with the TX antenna, and right next to this is a LO and IF distributor, and these are connected to a low frequency measurement receiver there, and you will convert the low frequency to a high frequency or the real frequency you are working on in your computer. The other interfacing components are exactly the same as before the direct RF. I'll skip this. And let me tell you about the sites of antenna measurement. Yeah, there are 2 pictures that show the indoor space and outdoor space. It is a matter of course, we prefer to put our antenna measurement system in the outdoor like this. This is the kind of ideal case. So if I afford the outdoor space, well, that's the best. But I actually, it is sometimes, most of the times, very inconvenient. Money-wise and the space-wise, it is very, very inconvenient. That's why there's an alternative solution, which is an anechoic chamber, as you see. The youngsters and young researchers who just stepped into the field of antennas and antenna measurement, now this picture and the shielding room, anechoic chamber, is going to be your friend and as soon as possible. Yeah, inside the walls are occupied with the ferrite or magnetic material based absorbers. So you can see absorbers, wedge absorbers, and you can see a horn antenna or reference antenna located here. And the walls should have the shielding effectiveness, which prevent the noise outside from entering to your antenna measurement space. Yeah, and it is related to the far field, especially to approximate the cylindrical surface or spherical surface with the planar surface. So there's a kind of a practical criterion. The phase angular difference between this is a arc of a sphere or arc of a cylinder, less than 22.5 degrees. But if the deviation between the point of the an arc from the planar surface, actually what that will cause a lot of error or high error, then you try to keep this number, and the difference between the a certain R here, this surface can be to be on the safe side approximated with the just planar surface, especially for near field scanning problems. When you replace the surface by the planar surface or cylindrical surface by the planar surface, yeah, but this is the topic you are interested in then. If this also gives us the message, if you have very highly directive antenna beam pattern, say for example, the beam width is less than 45 degrees, actually the cylindrical surface can be safely replaced by the planar surface like that. But the wavefront is diverging, which results in a broad beam width, then this approximation is going to be broken down. So then you cannot use that. Yeah, this is the message. And this is taken from the outdoor far field measurement site of my university. You can see a logarithmic, log periodic dipole antenna. This is used to measure the low frequency and wideband antenna performance. Though it is too far away from this receiving antenna, there's a source radiation which is located on the opposite side, and the wavefront, especially this cylindrical wavefront, starts to behave a planar wave. Then you can approximate the cylindrical wave or spherical wave from a distance with the planar surface like that. And outdoor test site is mimicked by this. Can you see a reflecting surface here whose edges are serrated? So these days, these serrated reflecting surfaces are quite common to imitate the far field. There's a man who's standing, then you can see and we can recognize how large this space is. Here, this is a source antenna, and the source antenna is directed to the surface of this reflector. Is behaves like an offset Cassegrain reflector antenna, and the spherical wave from the horn antenna is going to reflect the wave in the form of a plane wave. So you assume there being a quiet zone or planar wave side, planar wave, then you can check the antenna performance of the antenna on the aircraft. Actually, this is a scale model of an aircraft where there's an antenna which is located here, and that is going to be AUT, and this is going to be the receiving antenna, vice versa. This is a kind of a folded structure to mimic the enlarged structure by using the reflection of the reflector surface like this. The larger model and the smaller model, dependent upon the size of your D of your AUT or the frequency band like that. So here you cannot see the source antenna or a horn antenna here, which is hidden by this device. But there, horn antenna is going to shoot the electromagnetic wave, and it is going to be reflected to this way. That's the scheme. So it is called compact range chamber, or CATR in the industry. And here we focus on the shapes, two different types of shapes of reflecting surface. The surface is very smooth. It is called a blended rolled edge, CATR. So definitely these two reflecting surfaces face the horn antennas underneath, like the primary source of the offset cathode grain reflecting antenna, but they are just invisible now. But just focusing on the shapes of the reflective surfaces, the edges are smoothly rolled, so you can avoid unwanted edge diffraction. Edge diffraction is, but ideally, but it is not very ideal. And this, well, serrated edges is not very ideal, but practically these shapes and the serration and the rolling on the edges can suppress unwanted edge diffraction. So these two antennas are used for CATR these days, especially when millimeter wave antenna measurement is concerned. They would like to extend the distance of measurement or observation by using the CATR lately. Again, I have brought the CATR or compact rain chamber, which shows you kind of a fictitious space. This is a test zone, or called, let me go back. Oh, no, sorry. But it is placed on a later section. This is called the quiet zone. Quiet zone means the field behaves like a plane wave. So if there's a disturbance in the distribution plane wave, actually you can grab the field distribution and record it, and it's going to be the far field pattern of yours. This is the place, location of the horn antenna that shines the light, and that is reflected back to this area. And so what ideally they want to the bigger size of the unechoed chamber, but for economy, they can use this. So CR feed positioner, and CR means a compact rain chamber, and isolated concrete foundation. Usually you put absorbers on the floor, on the walls, even in the compact rain chamber. I'm holding my parabolic reflector, and it's a alternative solution, which is a planar reflecting surface. This is called reflector array, which you are going to see as soon as possible. Here, mentioning quiet zone again. In both cases, you can see quiet zone, which is a gray box here. Quiet zone is where your AUT is positioned. So here, planar wavefront, that is transformed by the reflection from the offset cathode grain antenna. In the CATR, this goes with the single reflection, but on the right-hand side, you can see double reflection. So it's a kind of a dual reflector antenna system. So there's a hyperbolic surface, and parabolic surface is the prime reflector. So this is a very interesting example of using the spaceborne antenna. Yeah, satellite communication system. You oftentimes see the dual reflector antenna system. This is sub-reflector. At the same time, on the left-hand side, this is the prime reflector of the system. Then the far field pattern of the horn antenna is its antenna gain is going to be increased also. There, this spherical wave is transformed again to planar wave. Then this is defined as a quiet zone. So you try to secure a wider quiet zone if you want to deal with the bigger millimeter wave antenna system, such as base station antenna or repeaters like that. And there's an example. If you have a horn antenna, and the antenna far field pattern is going to be just received at the receiving side, such as in the quiet zone. So now this antenna itself is tested. The antenna is a H-pole antenna, say for example. So the receiving antenna also has the correspondingly has the H-pole or horizontal polarization. This is a copolarization case. So the central region has the highest or maximum field intensity, the red. If you refer to the code color here, on your left side, these are the amplitudes, and on your right hand side, these are the phases. So just focusing on amplitudes of the horizontal polarization as the copole and vertical polarization as the cross polarization, the receiving antenna has the H-pole, and radiation source has the H-pole, then H and V are cross polarization. So there, the energy level goes down very fast. So where H-pole becomes maximum, V-pole becomes the minimum here. So for educational purposes, I brought these pictures. And the performance parameters of the test zone, this is a test site validation according to antenna measurement people who set up the devices or system there. They try to check these things, amplitude and the phase, especially amplitude variation and the phase variation along the azimuth and along the elevation surface like that. So the less ripple, the better. Now, I'm going with the near field antenna measurement. There will be 3 different surfaces to measure your antenna. The first is the planar near field. If you have an antenna with a high directionality or directivity, planar near field, the use is quite convenient. You can save your time. But if the wavefront is diverging from the source of radiation, actually, it is not highly recommended. Spherical wave for, the cylindrical wave for the fan beam antenna and the spherical wave, spherical surfaces for this pencil beam case, actually then you can use cylindrical surfaces and the spherical surfaces, which come later. But here, directional antennas are fine to go with the planar near field measurement. Practically, the gain should be larger than 15 dBi, and the maximum angle is less than 160 degrees. But practically, less than 90 degrees, then you can go with the planar near field antenna measurement system. So you can see a grid here. This grid means the probe. This is the probe. Can you see that? This is the probe, especially the open-ended waveguide. In industry, it is very common to use the the open-ended waveguide as the near field probe. So this is moving, or it is going to scan the space like that. So you can see points here, points on the grid. So points on the grid are sampling points, and you are going to capture the electric field, and you also rotate the open-ended waveguide from the horizontal polarization to the vertical polarization. And AUT, now you see a modified parabolic reflector antenna. Parabolic reflector antenna is known to give us a high directivity in terms of the antenna beam pattern. So there, what it is practically useful to use the planar near field scanning system like this. Then this is not the end. Near field captured on the surface is going to be transformed to the far field. Next is the cylindrical near field. This guy, the probe is going to rotate, go around the AUT. In the planar near field, you will ignore the back lobes. Sometimes you want to check the front to back ratio. Planar near field is not adoptable. Then you should go to cylindrical near field and spherical near field system. But you should check your time and your schedule and cost. Yeah, planar near field guarantees the small time or little time in measurement, but the big time is required with the spherical near field measurement. So it is quite crystal clear to see the differences. So for this antenna, actually, if you have the beam pattern, which shows you the fan beam, cylindrical wave, cylindrical near field surface is possible to use. But if your antenna, not like this, but actually this modified reflector antenna is known to give you the fan beam. But if you have an antenna system with the pencil beam, that requires you to use the spherical surface for the near field antenna measurement. So this works for every type of antenna, low gain, high gain, everything. And accuracy is the highest among the three things in wide or omnidirectional patterns on any antennas. And near field pattern here, we do not stop there. We should go on with the radiation integral under the frame of FFT processing and probe compensation like this. Yeah, and you can see the examples of the near field probe, and this is horn antenna, and the near field probe is quite close to the physical aperture here. This is the magnified or zoomed picture of the system, and this is after the calibration, the horn antenna calibration, and the probe calibration, this antenna is working. And again, the CR chamber, compact grain chamber is the replacement of the other far field patterns, but this still is under investigation about the validity. Skipping the other miscellaneous what things about that. Yeah, now I'm opening the chapter, a section of what examples, 5G beamforming antenna and material. Yeah.
Where's the cat?
Yeah. I'm here.
Sound is not coming over here? Okay. Okay. Professor Kang, you please listen to my question, then you answer, okay?
Yeah.
Because otherwise the audience cannot hear your voice. So you please take my question first, then I will mute for my computer and then you please answer. Question is, the near field technique, what you described in planar, cylindrical and spherical, right?
Yeah.
Yeah. So could you please tell that the modern Satimo or the other commercial products, they're using which type of things and why?
Yeah. Satimo uses what? Spherical surface. Spherical surface. Yeah. You can see there's a ring equipped with a lot of probes, and it is rotated. Then that covers azimuth and elevation at the same time on the spherical surface.
Well, so one more question.
Mm-hmm.
Suppose for typical X-band antenna or microstrip antenna in X-band, what is typical time taken by that system to measure its radiation pattern?
Please say that again. Question again, please.
Yes. Suppose it is an X-band antenna and
Expand antenna.
typical microstrip antenna. Okay.
Yeah.
So typical time to take data and give you the results.
The time and the results. Yeah. Let me see. Here. Yeah. Here you go. Yeah, microstrip patch antenna, which works for 31 gigahertz. And its far field pattern, which is hidden by the transmitter array or metamaterial lens. Underneath, there is a far field pattern of a patch antenna. So it is plotted in as the rectangular field plot. There are two results of a microstrip patch antenna. Near to far transformation result, there are two curves, and the other is the real far field pattern done in the CATR or compact range chamber. You can see the agreement between the two cases for one antenna. So these are the results of the microstrip patch antenna. When this is used as the seed or primary source of the metamaterial lens like this, then the gain here, you can see just above the 0 dBi, the gain is going to be amplified to something much larger. Yeah, gain increases around 15 dBs, and also beam tilting is possible like 20 degrees. So instead of using the microstrip array antenna, which requires us to have a power divider, you just put one simple patch antenna underneath, and above that microstrip patch antenna, the metamaterial lens can change the planar wave, diverging wavefront into converging wave like this. You can see that. So there's a jump in the antenna gain, and the antenna beam direction has changed to from 0 degree to 20 degrees or something. Or meta surface, this is a reflector array. You can change the angle of reflection. This is a normal incidence. Well, this is the system we built, so you can buy on your demand. We can shine the light from the source antenna. This is made out of a kind of a PCB structure. This is just a perfect electric conductor. But meta surface changes the direction of the angle of reflection to the receiver outside of the room. This is the wall. The meta surface is located inside of the room, and the beam can escape out of the room. So my research associate is waiting and capture the energy outside of the lecture room. So we can use handheld type, or we can use stationary probe type. You can see there's a jump. So at the expected angle of observation, we can detect the field. So microstrip patch antenna is extended to this type of new antenna, transmitter array or metamaterial lens, or horn antenna or patch antenna, whatever. You can put the primary source here, and the meta surface can do this job. while PEC or other poorly designed metasurface cannot do its job like this. So microstrip patch antenna case is that, but here you can see my beamforming antenna system for 28 gigahertz. Yeah, this one, you can see this is a multi-probe. I can change the direction of the beam here. This is the 28 gigahertz patch antenna. 28 gigahertz is the main frequency used in 5G mobile service in Korea and the United States. So here, patch antenna shows the far field pattern like this, 28 gigahertz. This also shows you just less than 0 dBi at that frequency. This is a near field plot. But if you run my beamforming antenna, which is made in the PCB structure like this, you can change the angle to 40 degrees or here around 10 degrees or minus 40 degrees like that. And near field electric field distribution tells you what happens, what will happen in the far field. So this is a near field for just a 10-degree tilting case, and minus 40-degree tilting case has this near field plot. So these are the examples, and microstrip structures can do this type of thing. Yeah, the far field patterns, which are actually, these are obtained by the numerical analysis, not measurement, but measurement was done with these examples as the case studies of my own. So you can, microstrip patch antenna here, yeah, a pair of transmitting and the receiving microstrip patch antennas. Yeah, there I could put my metamaterial multiplexer to select the channel. You can see the channel. There are 3 channels in the 3.5 gigahertz or sub 6 gigahertz bands for 5G mobile network. There you can choose one frequency or other frequency, second frequency, and third frequency like this. So this shows you how the electromagnetic field propagation occurs to the microstrip antennas. And also I could take the experiment to 64 COM, but actually the communication guys like these constellations. So for 60 COM quadrature amplitude modulation schemes, I tested them. Yeah, for in the aimed frequency bands, I could get the clear constellations, but other channels which I do not like to give my signals, blurry pictures were observed like that. And those studies were done with the lower frequency of the 5G, but for the high frequency in the 5G beamforming antenna system, I wanted to test the constellations or 64 COM configurations by checking the beam alignment, beam displacement, beam misalignment, or beam alignment for the beamforming antennas. So you can see the very clear COM constellations. All these antennas based upon microstrip patch antennas, which have the functions of the beamforming structures like that. Yeah, so Professor Kua, yeah, that means I'm approaching the end of my talk, right?
Yes. Yes.
So yeah, conclusions, you can read them, but I can tell you briefly what they were. Antenna measurement methods make you characterize your antennas, as in my case, knowing the pros and cons of different antenna measurement schemes in terms of accuracy and cost, you can find the optimal approach by applying antenna measurement methods to the 5G beamforming antenna and the metamaterial lens and cross-checking the different schemes in each case. The theories are well understood. Yeah, they are the conclusions. Questions or comments?
Yep. there is some interference issue, so we need to split our conversation. Let me finish first and then you'll answer.
Yeah.
The excellent talk, and you have covered wide range of modern techniques, traditional techniques, and several new challenges. So
Yeah.
from my audience today,
Yeah.
there are several questions. Definitely, we are not going to take all questions.
Yeah.
We'll have time to answer at least 2 or 3 questions from the audience.
I can.
Okay, so I'm asking few questions on your behalf. So the many researchers, students, they're sitting in the audience. So if you have any question, please. Well, so would you please clarify one thing that's my question too, that we have been familiar with both network analyzer and transmit and receive for standard antenna measurements in anechoic chamber. I think you also used these 2 types of setups. So
Right.
what's your impression? Which one is convenient, economic, and also in terms of accuracy, which one you prefer?
Yeah. Whether it is costly or cheap, I prefer the system with the vector network analyzer, but money-wise, I have to use my spectrum analyze with the signal generator. Then there are lots of things to do to validate and calibrate kind of things. So if you would like to grab amplitude and phase information at the same time, you should use vector network analyzer, or very, very special technique is required to change the amplitude only what results or data from spectrum analyzer to the complex numbers. I have developed my own method, but yeah, I prefer, and my students prefer, yeah, amplitude and phase data from the vector network analyzer first. But yeah, we should do mathematical jobs a lot for the spectrum analyzer based just amplitude only data. So yeah, that's my answer to your question.
Yes, I fully agree with you. And I have used, or I prefer the transmitter or the oscillator, and not like you, it is, you have used spectrum analyzer, I use power meter.
Yeah.
Power meter also serves you, but the spectrum analyzer is the better way. But you are very correct that the network analyzer, it needs lots of intermediate calculations.
Right. Yeah.
Optimizations and calculations. Okay.
I agree.
One more query is from the audience, that is, you already have shown the setup for aircraft measurements. Is it in free space or partially free space or full chamber?
Semi-anechoic, sometimes full anechoic chamber is most of the cases. It's a full anechoic chamber.
Is it typical thing that is used by Boeing and Hughes, the companies like this?
No. Yeah, that also what decides the money or the cost I have to pay for. Yeah, but if I have a good high gain antenna, actually practically I do not need the absorbers on the floor. Only the receiving side and the transmitting side, they should be surrounded with just absorbers. That's it. You can put your millimeter wave antenna setup, which uses the very high directivity antenna, then it doesn't have to be the full anechoic chamber system.
Thank you. I understand. So, please, any question? Please.
Sir, if we are measuring in gigahertz, 60 gigahertz, like 60 gigahertz, and I am having only amplitude data. So, what is the preferred method to calculate the phase data as well for the millimeter in the millimeter wavelength?
Professor Kua, please deliver his message to me.
Could you hear his voice?
No, not clearly.
The amplitude and phase data handling, probably that is your question.
Yes, sir.
In millimeter wave.
Instead of both amplitude and phase data, if I am having only amplitude data available with me.
Okay. The good question. That I don't have phase data. I have only amplitude data.
Oh.
So is it possible to get your the final measurement data or out?
Yeah. Actually, well, most of the cases, well, that's okay to go just with the amplitude, whether it is a millimeter wave antenna or just a low frequency antenna, that's fine. But for me, the Korean government gave me the mission to reconstruct the complex electromagnetic field distribution just based upon amplitude only. The reason is we had to reconstruct what in the IEC standard, there's a source reconstruction area. To do that, we need to make the phase part on the basis of the amplitude only area. The area is called power density area, power density measurement area. In the near field region, if you want to characterize the source of radiation, such as a mobile phone or base station antenna, quite in the vicinity of the physical aperture, actually, we need complex value, but amplitude only doesn't work, especially to know the power density. There, we should use kind of Hilbert transform or other mathematical approach to make or to predict phase term also. Then complex value on a surface is going to be used to reconstruct the source like that. It's a very tough.
Yes. Now your answer is very clear to the students. He was asking this question. That is the phase value. Come on.
No, I think.
What happened?
Me?
Connection.
Connection is a network issue.
Your problem, because here it is absolutely okay and
Well,
studies also.
Sir, Professor Kang.
Yeah.
So thank you for being with us and joining, sharing your experience and giving your valuable time today.
Yeah, I really enjoy that.
So thank you again on my personal behalf and on behalf of the organizers today.
Yeah.
And we expect you definitely in our December meeting in Bangalore.
Yeah.
Okay.
Just invite me as a speaker there too.
Yeah.
Thank you.
Surely we'll figure it out. Thank you. Bye.
I'm getting your fingers crossed.
Sure. Thank you.
Yeah. I hope you will.